We're going to revisit spectroscopy in relation to carbonyl compounds. So far we've talked about all six of these functional groups right here. And I just want to highlight, some of the spectroscopy features that each of them possesses. So starting with the carboxylic acid, have typically two key signatures that you have to pay attention in the infrared spectrum. The first one is a broad signal that usually starts above 3000 and oftentimes makes it past 3000 into the 2000s. That is very unmistakably, an OH signature from the carboxylic acid. But in addition to that, you also have to see a strong peak in the low 1700s, which correlates to the carbonyl carbon signal. Other examples of carboxylic acids are shown right here. You can see a very broad peak for the OH signature. And then you have your CO double bond in the low 1700s again. Here's one that also incorporates a nitrile. So you see the broad signal that starts above 3000, makes it past 3000, and you have the big signal at 1700. But in addition to it, you also notice or should notice a peak very close to 2300, which is basically the signature for the nitrile CN triple bond. Connections to aromatic rings are associated with values that drop down in the wave number signature, right? So your typical carboxylic acid falls in the low 1700s, but if the carboxylic acid is bound to an aromatic ring or an sp2 hybridized carbon, you see that the signal drops, right? In the case of the benzene ring, it drops down almost by a total of 100 inverse centimeter values, right? So we're now looking at something in the 1650, 1680 range. The acid anhydrides are kind of interesting because of the fact that you do have two CO double bonds, two carbonyls in the molecule. So it is not out of the question that when you look at the signatures for carbonyls, you tend to see two carbonyl signals. Now this one is a little bit broad, of course, because of the proximity of the two peaks, but they fall a little bit higher in the scale, right? The carboxylic acids were closer to 1700 itself, but for the acid anhydrides, we have now values that are more in the mid 1700s up to 1800 as well. All right, now here's another acid anhydride, and here you can see a much more prominent show of the two carbonyl peaks, in the mid 1700s and low 1800s. So be in mind about that. And then notice that I haven't really talked much about what was going on about 3000 because you don't have an OH in acid anhydrides. Now, sometimes you will see some little bumps showing up in that region, and that's usually because the anhydrides are still relatively hygroscopic, so they will acquire some water, and the older the sample, the more water you're gonna have there. So usually that's an impurity. So don't get tricked by that. Okay, your acid chlorides. One thing that absolutely stands out for acid chlorides is that the carbonyl peak falls in the 1800s through and through. There is no big signals above 3000 because there's no OHs. But yeah, 1800s is very common for acid chlorides. So here's another one, right? We have another acid chlorides that falls just slightly below 1800, but by all intents and purposes, 1800 is, roughly, where this is falling anyway. So the presence of that aromatic ring, helps drop it down a little bit. Esters are kind of intermediate in terms of where the carbonyl peak falls. They tend to be roughly in the 1750 range. So, the acid anhydrides give you 1750, 1800, roughly speaking, for the two peaks. Esters in the 1750 range. Acid chlorides are in the 1800 range, right? So maybe that'll help you remember those positions. And here's another ester, right? We see the same thing, close to 1750. Now the amides, the big difference right here is that the nitrogen is a lot less electronegative than oxygen. So donation of the lone pair on nitrogen onto the carbonyl carbon is a lot more predominant compared to oxygen. So what we see is that the peaks for amides tend to fall down in the mid 1600s. And if the nitrogen of the amide has hydrogens, you will see those broad peaks above 3000. In the case of two NHs, usually, not always, but usually you see two peaks, above 3000, which are both broad by default. If you only have one NH, then typically you only get to see one peak. However, there's one little caveat to this, and that is that, technically speaking, the rotation about this bond is semi-restricted because of the predominance of the lone pair of nitrogen to undergo resonance with the carbonyl carbon. So technically, this is kind of locked in place because you cannot create a double bond character between the nitrogen carbon bond here. And so when the nitrogen has the hydrogen pointing across the oxygen, in some cases, that will be one molecule that you get to see, but in other cases, the hydrogen will be pointing away from the oxygen, and the electronics are slightly different from each other. So that tends to also show you two different peaks in those situations. The same thing goes for the carbonyls in those cases, right? Because you're technically looking at two variations of the same molecule. Okay, and then for one situation in which the amide doesn't have any NHs, then don't expect to see any broad peaks above 3000. And then here we only see one single carbonyl peak because the group on the top and the group on the bottom are literally the same thing. So it doesn't matter, which one is pointing towards the oxygen. They're both the same, so it's the same story. Okay, so yeah, just keep that in mind. 1600s, mid 1600s for amides, they tend to be on the low end. And then the nitriles, we can already pointed out that the triple bonds falls around 2300 in the spectrum, right? And the peaks vary in terms of intensity. Some of them can be kind of weak, like this one. Other ones can be relatively strong, like that one there. It really varies from sample to sample, and also how the sample is prepared. So just don't get too hung up on how intense the peak is or how not intense it may happen to be, right? The also impurities are also potential things you may see in spectra of nitriles because you tend to make miscible aqueous solutions with nitriles, at least the ones that have low carbon content. All right, so hopefully that will help you out in identifying some of these compounds in the future. There's some key proton NMR signals that you should probably know, like carboxylic acid, OHs fall roughly around 12 ppm, right? But the rest of the other ones never have an OH necessarily present. And then even the NHs of the amides, those are like between 3 and 5, but can differ a little bit from sample to sample. Okay, so in the next lecture, we're going to start talking about, or the next video, I should say, we're going to start talking about the actual reactions. So have your notebooks ready because here's where things get interesting. Okay, see you next. Bye-bye.